Let's go ahead and look at a problem where we're looking at the pH, finding the pH of a buffered solution. So this is very similar to finding the pH when a common ion is used. So they're essentially the same thing. So in previous slides, I have done that, and we're just going to do it again here. So this is a buffer solution, contains acetic acid and sodium acetate. Notice the common ion right there, that acetate ion, and it says calculate the pH of the solution. So let's first start off with an equation. I always like something I can hang my hat on just to figure out what's going on. So this is an organic acid. It is going to release that hydrogen ion, and then going to have a leftover. And then we know that we're going to add extra of this. And so I'm going to set up an ice chart. So I write my equation and I do my ice chart, and let's look at initial values. So initial values, this is 0.5. And it also says that this is 0.5. So this is at the beginning where I have all of these. My acid hasn't dissociated yet, so I am going to have 0 of that hydrogen ion. Then let's look at the change. So we know that this is going to lose a little bit, and this is going to gain a little bit as it dissociates. So I can bring all this down. And I am going to write my Ka expression. This is for an acid, so I'll have a Ka. Products multiplied. Oh, I wrote this equation wrong. Sorry. Let's take off that hydrogen. Okay, now that's correct. So products on the top divided by reactants. So there's my weak acid, and then I'm going to plug in what I know. We do know the Ka because they gave it to us. 1.8 times 10 to the minus 5. And my hydrogen ion concentration is going to be X. And this one's going to be 0.5 plus X. So in a normal acid reaction, these two values are going to be the same, the hydrogen ion and then the conjugate base. But because we're in a buffered situation, we have extra of that conjugate base. Here's our conjugate base. So we can see that we just have the values are a little bit different. Okay, so we put what we have. We're going to assume the shortcut rule. So I'm going to assume that this is tiny and that this is tiny also. So I'm going to eliminate it. Now look what this does to our math. So this one just so happens to match. So 0.5 on top and a 0.5 on the bottom is going to cancel out. So I am left with X, which is the hydrogen ion concentration. So this would be 1.8 times 10 to the minus 5. Okay. So notice that when the conjugate base and the weak acid, when they have the same concentration, which they do here, then I know that my hydrogen ion will be equal to my Ka when those are the same. All right, so we still need to find the pH. So the pH is equal to the negative log of the hydrogen ion. And plugging that into my calculator, I get 4.74. This is that pH of that buffer solution. They used to, on the AP test, make you calculate the pH if they added a little bit of acid or if they added a little bit of base, but that has been taken out of the what is expected in the AP test. So these problems are actually only this hard, what I've showed you. So you should be able to look at a problem such as this and figure out what the pH of your buffered solution is at the beginning. And then they might have you graph it, but you should be able to figure out initial pH before anything has happened. Now, would you like to know an easier way to do this without an ice chart? That is the next slide. So this is another way to calculate the pH of a buffer system. And I call it the Rossiter equation because this doesn't really have a name. But here is that dissociation equation for an acid. And if I rearrange it, So I get the hydrogen ion on one side. This is the Roster equation. So this is something you can memorize, or you can just derive it from the Ka. This is actually on your data sheet. So you can just rearrange it to solve for the hydrogen ion concentration, which is what we're interested in. The second part of this is once you find the H plus, you are going to just take the negative log. That's a negative. The negative log of the hydrogen ion concentration, and then you'll have your pH. So again, this equation is very useful to calculate the pH of solutions when you know both the weak acid and the conjugate base, so when they are known. Now, when you take the negative log of both sides, you get this equation. And I find students really mess up with this equation. So it's kind of confusing. You don't know what goes where, but this is also on your data sheet. They took it away for a few years, but they've just recently put it back. It's called the Henderson-Hasselbalch equation. You can use this one just like you can use the Rossiter equation. Again, the Rossiter equation is this one right here where you're solving for the hydrogen ion concentration. But either way, so again, on your data sheet, it actually looks like this one right here. Okay, the pH equals the pKa plus the log of the conjugate base divided by that weak acid. Remember, anytime you see a P in front of something, then that means they've taken the negative log of it. So the negative log of the Ka, or that acid dissociation equation, is called the pKa. But this is very helpful to calculate the pH because we always take that shortcut with the X's. Then we don't even have to really worry about doing an ice chart. So let me show you an example of this. So again, here's the Roster equation. It's just that Ka equation rearranged, and I'm just going to plug in what I know. So to find the hydrogen ion concentration, again, so I can find the pH in the next step, I'm going to take the Ka, and then I'm going to multiply it by this fraction. So I have, this is my acid up above. So here's my acid right there. So 0.75. So with buffers, it's good for them to have the same concentration, but sometimes it doesn't always work out that way. Their strongest buffers will have equal parts of the weak acid and its conjugate base, or its weak base and its conjugate acid. But so if they're equal amounts, it just gives it it's just a better buffer, but it is possible that you can have different concentrations. So this just ends up being a math problem here. But notice I didn't have to do that big long ice chart, which is kind of a relief. When I do my math, I get 4.2 times 10 to the minus 4. Remember, this is the hydrogen concentration. So to take the pH, I take the negative log of this number, and I get a pH of 3.37. So again, no ice chart, just have to do this Rossiter equation and then take the pH. You also could do that other equation that's on your data sheet, but again, I find that students, they get really confused with their math. This seems easier because you don't have to add and divide, you're just multiplying and dividing. Let's look at buffer capacity. So how many protons, which are hydrogen ions, or how many hydroxide ions could a buffer absorb? Well, it's called buffer capacity. So you have a higher buffer capacity if you have a higher concentration, and you have a lower buffer capacity if you have a lower concentration. And again, the best buffers are when they have equal amounts of the weak acid and its conjugate. All right, so looking at these two, I have solution A and solution B. So first of all, they both would be a buffer system. And the reason why I know that they're a buffer is they have a common ion. The difference here, actually there's a typo there. Let me just scribble that out. Okay, the difference here is you have that acetate ion. So it just has a 1 proton difference. As long as it's just a 1 proton difference, in this case it's lost a proton. In other cases it will have gained a proton, and you can't gain or lose 2. It's always just 1. So you can tell that that is a common ion because it matches up, and this one is the same one. Okay, so they're both buffers, but as far as which one is the best buffer, it's going to be the one that has the highest concentration, so it's going to be this first one. So even though they're not the same concentration, um, it there is more, so it can absorb more protons and more hydroxide ions. So let's look at designing a buffer. This is part of the AP skills that you need. So you need to be able to evaluate buffers, just like I did that last slide, and perhaps design them. So the best buffers have equal concentrations, and when they have equal concentrations, according to the Rossiter equation, if these two are equal, you can cancel them out, and you end up with the hydrogen ion concentration being equal to the Ka. Or if you were to take the log of it, the negative log of both sides, you would get the pH equals the pKa. So how you would design your buffers, you would look up the Ka, and sometimes they would even give you the pKa. And if they gave you the pKa, then this is the pH that the buffer works best in. So if you want to design a buffer to be at a pH of 3, then you're going to look at each of these Kas and you'll find their pKa. Or really, you can simplify things and look at the exponent. So I know this first one is going to be a pH of probably between 4 and 5. And the one down below is going to be a pH between a 3 and a 4. I think it actually ends up having a pKa of 3.17 if you actually do the math. But you could, again, just look at the exponents to give you an approximation. But if I were to pick a buffer for a pH of 3, I would pick this last one. So this HF. So I would have an HF buffer and I would design it. So I would have lots of HF, and then I would have something that had fluoride ion in it. So maybe do an NaF salt. So in this case, it just has that common ion there. So I know I would have extra of this guy to help make that buffer work. So this is what the AP board calls design a buffer, where you match the Ka to the pH you want. And I think I went over this, so let's just go over it quickly. pH versus pKa, it just means that you've taken the negative log of your hydrogen ion, that's how you get the pH, and your pKa is the negative log of your Ka, your acid dissociation constant. The pH measures the acidity or the power of the hydrogen ion, and again, if it's low, it's more acidic. The pKa measures the strength of an acid. If you have a lower number, you have a stronger acid. So here's all the three equations that we talked about in this section. The relationship between pH and pKa, and you can figure this all mathematically. So if you're looking at this and are you kind of confused, you can just do a math problem and then plug in fake numbers. What would happen if you had more weak acid than you would its conjugate base, or vice versa? If you get a pH that is lower than the pKa, then you know that the acid has a higher concentration. So I like the Rossiter equation, which is this one. So looking at this mathematically, if I had a pH that was lower, so that means it would have more power. So this one would be higher, this one would be lower. That means that my acid would have to be larger and my conjugate base would have to be smaller. And vice versa. If my pH is quite large, so that means it would be basic maybe, or at least like a 4 or a 5, then that means the pK would be smaller. And so you'd have vice versa. You'd have your conjugate base would have a higher concentration. Again, plug in fake numbers and you can see the relationship here for this. What is the relationship between pKa and pKb? You get a pKw. Notice that this is similar to your pH equation where 14 is equal to pH plus the pOH.